All right, my name's Davis Shell, and this is my midterm for Physics 208C. Today I'm going to be talking about the uncertainty principle and how it relates to the wave-like properties of particles. So, our first example, I'm going to start by thinking of a particle as a beat of multiple waves. So as you can see, the waves will constructively and destructively interfere with each other to create a beat. And as we add more and more waves, we'll end up with just a beat with one big amplitude. Here. And this would be delta x. So here we can see that with many multiple waves, we're very certain of the position of where the particle is. But when we have so many waves, there's so many different lambdas. And as we know, equation P is equal to h over lambda. The momentum is equal to h over lambda. So when we're certain about the position, we won't know anything about the momentum. But if we have just one wave, it won't produce a beat, so we won't know anything about the position of the particle, but we will know lambda and therefore know the momentum. Alright, that's my first example. Next, I would like to look at an experiment where we have single slit diffraction and we're shooting electrons through the single slit. This is A. And when electrons are shot through the single slit, we see an interference pattern much like that of a wave. So we have areas where there are no electrons because their electrons are interfering with themselves destructively, and then areas where there's multiple electrons. So we'll have this. And our uncertainty in position is going to be equal to the A here. So we'll call this delta Y. And we can consider the momentum of one of the electrons here as P. So here's P. And then the uncertainty of the momentum will be this here. Delta P. And we can draw up a triangle here where we have P, delta P, and then here is our new P. And for small angles, we can see that sine theta is approximately equal to tangent theta, which is approximately equal to delta P over P. And from Physics 208B, we know that is also equal to lambda over A. So, and A is equal to delta Y here. So we can say delta P over P is equal to lambda over delta Y. Cross multiplying, we get delta P, delta Y is equal to P lambda, but then remember that P is equal to h over lambda, so we can sub that in. Delta P, delta Y is equal to h over lambda. Lambdas cancel out. We get delta P, delta Y is equal to h. And we can see that we can have an uncertainty from on this side of the triangle or on the other side as well, so we're off by a factor of 2. So delta P delta Y equals h over 2, which is very similar and proves the uncertainty principle from what we got in our other example here. So yeah, that is how the uncertainty principle relates to the wave-like properties of particles, and they're kind of one and the same. Thank you.